think it was, yeah, it was Tuesday. I finally finished. I started grading some more over the weekend. I kept getting interfered with, and I just couldn't get it done. So I ended up grading the remaining introduction to labs. I ended up grading those on, I think it was Tuesday, is where I finally finished them. So everybody's is now graded. There's now two columns, one of which is just intro to lab. The other one, I had originally made it intro to lab with a little asterisk after it, but after that I said does not count in your grade. I had to leave that column because those that turned it in there uh, need that column so that they can access their old labs to see it, and so they can see my comments that I typed in there about those labs. So you need that. And then I just took the grade and copied it into the other lab column. So make sure y'all check those things out. Make sure you read. Sometimes I post comments directly on the lab report. So you'll see little notes listed on the lab report, and then you'll also see boxes of comments off to the right. At least that's the way I see it in my view. So make sure you check those out so you'll get the full understanding of what I was saying. Sometimes, like I tried to tell everyone that when you turn in a lab, you guys, what you're doing in your lab, more or less on your own. You don't necessarily have lab partners. So I structured the message that I normally give all my students in such a way that they knew that sometimes you don't have a partner, but the main thing is you need your name on the first page of your lab report, and then you want to say no lab partners or no one assisted. If you had someone, that did assist, even if they weren't in the class, it's still better to put that they assisted. So you could just give me your, say my brother, or you can say, Billy C or something like that. If need be, I would ask you about it. But you just want to get into the habit of whoever's working with you, you want to make sure you have a record that they were there so that if something seems funny a little bit later, you can one ask them for any issues that might have came up or see if their memory is something. But sometimes it just turns out to be, hey, this particular person was later caught, falsifying data or something, and now we need to see what parts of the experiment the person had the role in which case you might have to completely throw away the results and call your paper back. That's what happened with, to some extent, with Andrew Wakefield, who basically tried to tell everybody that vaccines cause autism. Oddly enough, he happened to be working on a new vaccine that didn't have thimerosal in it at the same time. It's almost like he had a reason to do it other than the well-being of the children in Great Britain. But as far as I know, he's still a practicing doctor. He lost his license in Great Britain. I think the last I heard, it looked like he might have lost them in Florida, but I think he's in Texas now. But anyways, that's the big deal with science is your honor is really, really important. So you've got to make sure you're upright and completely straightforward and crossing all your T's and dotting all your I's. All right, it's definitely time to get started. So I'm going to go ahead and get started. We are going into chapter four. Ask anybody if they had any questions. I'll ask again. Does anybody have any questions on any material? Okay, as I said, I probably will work some more chapter three problems and make videos of them. For instance, I had a couple students in my face-to-face class today ask questions about chapter three, and one of the questions was a really good one. So I'll probably do something like that problem for you guys so y'all see it. But the main thing I'm doing is I'm going to go ahead and jump right back in to chapter four. So we're starting right off with chapter four. I'm going to go ahead and share my iPad screen with you guys before I forget, of course. So it should be coming up there any minute, and I've filled my notes up already for the first page and a half. So you don't have to feel obligated to copy all this, but at some point you're going to have to copy all this. And I actually just copied it straight from the book, but I added some comments and stuff of that sort. Just a good rule of thumb. If something says law, at least in the physical sciences, if something says law in its name, I would just go ahead and commit that exactly to memory. Okay. In this case, we actually have a whole chapter called Newton's Laws of Motion. So that's another indicator. If something takes up a whole chapter or even a whole subsection in a chapter, then you should probably commit it to memory, and that's the case here. So I said commit to memory Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. And then I stated them. Every object continues in its state of rest or of uniform velocity as long as no net force acts on it. That's Newton's first law of motion, which really came from Galileo, who had worked it out as a law of inertia. And he said an object in motion tends to stay in that state of motion unless acted upon by a net external force. And he would say as well that it was as if the object had some quantity called inertia. And that was sort of just a word that makes you feel a little bit better about going smacking Aristotle in the face, because Aristotle had taught everyone that objects basically have natural motion and they have force motion. And the force motion is what happens when objects are not being moved from a place towards their natural place. So remember the four elements: earth, wind, fire, and water. And the fifth, if you wanted to count, like I said 1,000 times before, Mila Jovovich in the movie The Fifth Element, starring her and Die Hard, Bruce Willis. Yeah, Bruce Willis was in that one as well. So it was probably me, Bruce, and Mila, who are the only people that saw that movie. But anyways, the fifth element is ostensibly Mila Jovovich, but really what they meant is the heavens. So there's a fifth element that's the heavens, and that would behave perfectly. So the forced motion was any kind of motion where an object wasn't trying to get to its natural place. So you, for instance, would look at a rock. It's part earth, so its natural place is the center of the earth. And yes, they understood that the earth was spherical, not flat, but its natural place was getting to the center of the earth. So if you let go of a rock, it will suffer natural motion going downward towards the center of the earth. And what Aristotle taught us was that the rate at which it fell towards the center of the earth was directly related to how heavy it was. So if you had, a 100-pound rock, it would fall at one rate. But if you had a 200-pound rock, it would fall twice as fast, and a 300-pound rock three times as fast, so on and so forth. But if you wanted to move the rock sideways, you had to continuously apply a force to it because that was violent motion. That also explained, for instance, smoke, which is what comes from burning of, let's say, wood, which wood is partly earth, but if you look closely, it's partly air. So it's got a little air in it. It's got a little, which is, one of the three elements. It's got a little earth in it, which is another one of the three elements. And it's got a little fire in it, which is another one of the, I keep saying three elements, so another one of the four elements. And because of that, it sort of has a natural place. The fire is like our sun is a fire. It's up above our atmosphere. The air is above our earth. And the earth, which is what the part of the tree is made out of, in addition to air, is more like the earth. So its natural place is the center. So smoke lifts up, but it doesn't lift up quite as fast as you might expect if it was pure fire. Nor does it fall like you'd expect for Earth, because it's mostly air and fire and less Earth. So they had some very strict rules about that, and it worked somewhat consistently. You'll be surprised how many times throughout the semester you'll make conclusions that are blatantly Aristotelian as opposed to Newtonian. But either way, Galileo was well aware that the world wouldn't necessarily be willing to accept whatever he's teaching and learning, strictly because they, hold Aristotle in such high esteem. And also, by the way, by this time, the entire government, which was based in religion, had its whole church and the whole Bible interpreted in terms of those Aristotelian laws. So it was a really, really, really big deal to try to subvert them or change them around. So, anyways, that's what Galileo gave us. And like I said, he used the word inertia. And we use that now, only we use it as another word for mass, but it really is an object's reluctance to accelerate. So the Newton's first law is every object continues in its state of rest or of uniform velocity as long as no net force acts on it. You can also say that, like I said, an object in motion tends to stay in that state of motion unless acted upon by a net external force. Or you could also say more succinctly, since you've learned about vectors, Galileo knew nothing of vectors, Newton knew nothing of vectors. They were all created in the 1800s, early 18 to mid 1800s by two different people simultaneously. But either way, they didn't have that, but we do. So we can say an object will maintain a constant velocity unless acted upon by a net external force. And I'm saying net because it's not okay to just take a single force and use that to figure out whether the thing is moving or not. You have to take the sum of all the forces acting on the object, and that sum is technically a vector sum, so that's a little more complicated. But still, the vector sum of all the forces acting on the object, if that's zero, then the velocity will remain constant, and that velocity could be zero. Okay, but that velocity could also be 60 miles per hour horizontal and due north. So that gets it in three dimensions exactly the direction we're talking about. Of course, the Earth is rotating, so even that's not necessarily that clear. But the main thing is you see that that's what I mean by constant velocity. It's magnitude and direction as a constant. So constant velocity is a hallmark of the net external force being zero. Uh, and Aristotle's wrong. You don't need a force to sustain motion. It's naturally going to sustain it itself because of the laws of motion, specifically Newton's first law. Newton's second law says the acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to the object's mass. The direction of the acceleration is in the direction of the net force acting on the object. So that's a lot of sentences, and I want to explain to you what he's saying here. And you know, they didn't necessarily have a good typesetter in the time that Newton wrote his Principia. So it was really hard to write a lot of equations, and it was also hard to do a lot of calculations. So Newton ends up using equations, but he also ends up using a butt ton of geometry to solve problems. If you look at a copy of Newton's Principia, it's about that thick. So it's a really thick compendium of everything we had discovered about the laws of physics at that time, and most of which was worked out in great detail by Newton. And he was, as he stated in a fairly famous quote, if I have seen further than others, only because I stood on the shoulders of giants. He was, in fact, being somewhat humble there, but he was also sort of dissing Robert Hooke, who was the head of the National or the Royal Society and one of his arch enemies. And he had a bit of a short man complex. He was well under 5 foot tall, as best we can tell. Kind of a well, we don't know what he's looked like because, oddly enough, everybody that's ever been a president of the Royal Society has a painting that we can look at to see who they were and what they look like, except for Robert Hooke. And who was the president right after Robert Hooke was one uh, Isaac Newton. So we suspect Isaac Newton is the one that destroyed the picture of Hooke. So we have no idea what Hooke looks like. But he was a really, really good scientist. He just wasn't a Newton, but you know, who is? So, anyways, he was saying, if I have seen further than others, only because I stood on the shoulders of giants, not hobbits like you, Mr. Hook. So you can take it like that. Now, what I wanted to point out to you in grade school, like in high school, Algebra 1, for instance, when we use the phrase directly proportional, what we would say is A is directly proportional to, in this case, we're talking about the net force. So I put this sigma here because that's the mathematical symbol that means add them all up, right? So we're considering all the forces acting on the object. That's what they are. And we're saying that it's proportional to A. This is what I call thumbs up, thumbs up. What I mean by that is if one goes up, the other goes up. And if we know for a fact the exponents are both one, then if I double one, then I double the other. If I triple one, I triple the other. So what we're saying here is if I triple the total force, then I will triple the acceleration. If I cut the total force in half, then I will cut the acceleration in half. Now, it also says inversely proportional to the object's mass. So this is what inversely proportional means, and this is what I call thumbs up, thumbs down. Okay. What you have is the A on one side in the numerator. There's no fraction there, so you can automatically write A over 1, and you'd see A is in the numerator. And then on the other side of what would be the equal symbol, you have an M, but it's in the denominator. So when you got two things on opposite sides of the equals, but they're on the same side of the fraction, that's thumbs up, thumbs up. But if you have two things that are on opposite sides of the equal, and one is on the numerator and the other one's on the denominator, then it's thumbs up, thumbs down. What that means is as one goes up, the other goes down. So if, for instance, I double the mass of, let's say, a ball, let's take it from a baseball to a softball, and let's say that roughly a softball is twice as heavy as a baseball. Probably not that accurate to say that, but just you know that the purpose of a softball was to slow the ball down a little bit, so we can just go with that. But by increasing the mass by a factor of two, that means mass is going up by two, but the other thing is thumbs down, so that must be going down by a factor of one half. In other words, you're dividing by two. So that's what ultimately we can conclude by directly proportional and inversely proportional, or yeah, inversely proportional. So we put those two things together, and normally the way you do that is you would say A is equal to some constant times F. I'm sorry, I'm trying to get this to keep writing while I'm writing. We're just going to say A is equal to some constant times the summation of forces and inversely proportional to M, right? We'd put that K in there and then we'd use some data to figure out what K is. Well, what we did in this case is we chose to make that K 1. So we don't have a K. In fact, all we have is that the acceleration is equal to 1 over the mass times the net external force. And notice these vector symbols. Because of this vector symbol, A is proportional to F, tells us the same thing. The direction of the acceleration is in the direction of the net force. So Newton's second law as a vector equation, we can write it like this, and that gives us everything we need to know because we know A is just being multiplied by a scalar M and mass can't be negative. So that means A is parallel to MA. And since on the other side the equal is the net force acting on the system, then this vector has to be parallel to that vector because for two vectors to be equal, they must have the same magnitude and direction. Okay. And now, what's amazing about vectors, one of the many things that's amazing about vectors, is that very succinctly has one equation that now speaks for three. And in fact, if you go to solve a physics problem, you're going to have to, one, make up, in many cases, you're going to have to, one, make up a XY coordinate or even an XYZ coordinate system. And then you're going to have to break all the vectors down into components in the x direction, components in the y direction, components in the z direction. And then you're going to apply Newton's second law for each of those dimensions. Now, most of this book is going to be dealing with two-dimensional stuff, but occasionally we can bring in a third dimension, but it really introduces not very much complications to it. Okay? So that's Newton's second law. And then Newton's third law, it says whenever one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first. Okay, that's pretty close to what you're used to hearing. For every action, there's an equal but opposite reaction. But I think every action, there's an equal but opposite reaction. Unless you're in the know, I don't think you understand what that says. Okay, so I tried to put it in a more even more straightforward way, which I think the sentences did really good, but we can reverse that, or we can maybe make that a little more specific by giving it vectors. So what I said was FAB vector, so it's got a vector symbol over it, it's got a little arrow, is equal to negative FBA. Now, whenever you see a force with two indices or two suffixes on it, two subscripts on it. I said suffix. Whenever you see a force with two subscripts on it, the first one is the object feeling the force, and the second one is the object doing the force. So FAB means the force on object A due to object B. And then that is equal to the negative of the force on object B due to object A. So hopefully, I think you can see that that's exactly what the sentences above it meant. Any questions on that? Okay. Your book goes over some interesting examples. I want to point out a couple things. So right now, you can look, and I have this notepad here, and it was laying on my desk, and there's a calculator laying on it, and there's a notepad laying on it, and there's some pens laying on it, right? Right now, what we see is the object is sitting perfectly still. That means its velocity zero, and its velocity still zero, and its velocity still zero. So we know the acceleration is zero. So we're definitely in a Newton's first law scenario. Every object continues in a state of rest. That's what we're doing here. Are of uniform velocity as long as the net force acting on it is zero. So I'm picturing this calculator. Let's focus on the calculator. And we're thinking about it sitting on a desk as opposed to on this notepad in my hand. So I'm bringing it back down so I can put it on the desk. You can just take your calculator on your desk or your phone or whatever, and you look at it and you realize it's not accelerating. It's actually sitting perfectly still. So the net force on it is clearly zero. Now, can you tell me any force that might be acting on, just one force is all I need, any force that might be acting on your cell phone or my calculator? And I'm going to go ahead and make sure my chat window pops up. Oh, there it is. Yes, gravity. Yeah, that was a pretty good movie. Yes, Gravity was the one I'm thinking of. Everybody knows gravity's pulling on something. So, in fact, gravity is the attraction of an object to its, local planet, moon. If it happened to be on a really big comet or asteroid, it would be to that. But the biggest body around, which is monumentally larger than the object itself, if the object we're thinking about having weight is on a huge object, the gravitational attraction of the object we're thinking of having weight is that actual force of gravitational attraction to that bigger body. Okay. So, with that in mind, yes, we know for a fact that gravity's acting on it. But we can now use Newton's first law to realize, wait a second, there must be another force acting on our calculator. A lot of people don't realize this force necessarily exists, and it sort of seems like, hey, this force is uh, weird because in this case, a table, my desk, which is an inanimate object, is actually pushing up on this calculator. And the reason why we can make that conclusion is because the net force must be zero, and we know one force is acting on it, and that's gravity acting down. So if gravity's acting down on it, something's got to cancel that force out. That turns out to be what we call the normal force. Normal, which is the mathematical term for a force that's perpendicular to a plane. So you'd call it normal instead of using the word perpendicular. So the normal force is a force perpendicular to the surface, and you might not think of a table as being able to do that, but remember, a table is just a geometric construct that has a specific shape that makes it be able to stand upright on what you'd call its legs. So you could take, for instance, my Rubik's Cube, and you could sort of picture this top surface as a table, and this edge, and this edge, and this edge, and this edge as legs. So, because it's made solidly in such a way, I can lay it down on a surface like on my hand, and the top surface will stay level. And then I can apply a big force on it, and it stays level anyways. And I can apply a bigger force, and it stays level anyways. So that's what's going on with this calculator. So if you think about the calculator sitting on the table, it's not that the table necessarily has to actively put out a force. It just has to do what it was designed to do, which was sit perfectly still and hold up the surface. And if you consider it further by changing this slowly into something more heavy, so you could imagine maybe in replacing the calculator with something that was like a rectangular box, exactly the size of the calculator, and you could slowly pour sand into it, and that column could get, hundreds of feet tall, and eventually the desk is going to break. Or, like I tell my students in class, you could just take an elephant and let them sit on the desk, and you'd quickly see that, oh, the desk must have been supplying a force earlier because it wasn't sufficient to supply the force when the elephant sat on it. Okay, so that's one of the neat things you can use with Newton's second law is if you see an object that's not accelerating and you only know of one force acting on it, then you know there must be another force at least acting on it to cancel that one out. Okay. Also, if you see an object that is accelerating, then you know there must be an unequal or unequilibrated number of forces acting on it such that it has a net external force acting on it. So that's something you can do with the Newton's first law. The Newton's second law is once you've figured out that an object is actually being or experiencing a net external force, and I say external because I want you to get out of the idea of thinking that you can lift yourself up by your own bootstraps, which is a wonderful philosophical idea and it's great for human endeavors. But the main thing is, if you actually tried to pick yourself up by your own bootstraps, you just couldn't do it. Okay, because basically there's no force. That you can apply to yourself that would separate yourself from yourself other than taking a skill saw and maybe cutting across your belly or something terrible like that. So don't do that. That would be bad. All right. So mainly what we do is we use Newton's second law when we want to know either the mass or one of the forces or the net force or the acceleration, and it tells us how those things combine to uh, to relate to each other so that you can find whichever one you don't know. The third law, for every action there's equal but opposite reaction, or in this case, FAB equals negative FBA. Now, what that means doesn't seem as obvious, but I usually use the scenario of something you probably saw when you're in high school. Inevitably, some kid's going to get mad and they're going to punch something, some inanimate object, whether it be a locker or a wall at a party or something like that. And I just want to point out to you that our thinking as the caveman that we may or may not have used to been in in previous generations of our humans. Okay, we think about forces and violence and things like that, and protection and fear and all that kind of thing. So, in some sense, that Cro-Magnon sort of brain might think to you, hey, if I can punch that wall hard enough, then the wall will break and I've sort of won. Well, if you do a series of experiments and discover that in order to break a particular part of the wall that you plan on punching, let's say it's a part with a 2x4 or 2x6 behind it, it takes 700 pounds of force. Okay. Let's say a bunch of experiments have shown us that. Well, in our high school brains, unless we were people that knew physics or understood science in general, in our high school brains, it's not uncommon for me to think, well, if I can punch it and break it, it won't hurt me at all because I'm big enough to do it. But you're dead wrong because if it takes, by experiment, 700 pounds to break it and you hit it and you break it, guess what? You are applying a force of 700 pounds to the wall by you punching it. But according to Newton's third law, the wall is going to put exactly that force back on your fist. Okay. That's why boxers occasionally break these bones in their hands and stuff like that. That Total Recall scene with Arnold Schwarzenegger punching through a car windshield. That can totally happen, but it's also very common that when you do that with punching with that much force, sometimes your bones break instead or in addition to it. Okay, so that's one ramification of Newton's third law. Another one is a little less obvious to see, but if you've ever tried to kill a fly in the air, so I know this is death and we're talking about killing things and there's no reason for it except the thing keeps pestering you and trying to keep you from sleeping or something. But still, let's just bear with me a second here. We run around with a fly swatter, especially in the summer, especially if we got the windows open, because flies will get in your house. And you'll take this fly swatter, and if he's on the table, you can smack him, and it will kill him. And that's all well and good. But, well, again, somewhat well and good. But if you instead try to hit him in the air, what often happens, and I've done this a lot of times, and I used to think about it back before had any understanding of physics, because remember, I never even took a physics class until I got to college. But basically, if I go and smack a fly really, really hard, as I've done, what I see often happens is sometimes I'll hit that fly and it'll fly across the room and bounce off the wall and it'll fly a little stunted for a second. You'll see him sometimes fall down and then get up and fly and he's doing a little weird pattern or something. And it's kind of, I don't know, emasculating because you took all your power and you beat the poop out of a fly and he just sort of flies off like, well, what an idiot, right? Like, why's that guy got to be so mean, right? Well, there's an answer to it, and the simplest way of saying the answer, though it doesn't really give you much satisfaction, is that Newton's third law is the reason you can't apply much of a force to it. And what I mean by that is no matter what force I can apply to that fly has to be able to apply that same force to me because Newton's third law says it's going to. So, in a very superficial sort of way, you can think, well, I can't imagine a fly putting a huge force on my hand, so I can't imagine me putting a huge force on a fly, is really the correct conclusion. Now, let me make that a little less weak and explain the gory details. So the gory details are that acceleration is the change in velocity divided by the change in time. So if you imagine, let's say, a fly hovering in space, let's say this is a fly. It's a big fly. I don't mean this big of a fly. I just mean a regular fly, which might weigh on the order of a couple grams or something like that, right? So this is supposed to be an itty bitty fly. This is supposed to be my hand. If you say I'm like a college level baseball pitcher, like the one that we had at University of Tennessee a couple years ago, and he was throwing like 105, 107 mile per hour fastballs, then you can imagine I could be a person whose hand could move at 107 miles per hour, say. So if I go to hit this bug, this fly in the sky or in the air, what's going to happen is the fly could be just sitting here. My hand comes by and hits it, and my hand is moving now at 107 miles per hour. Immediately, the fly's body gets squished just a little bit, maybe a lot. Maybe he has a little accident, pees and poops on himself because you squished him and startled him so badly, but not necessarily hard enough to completely kill him. And I'll explain why in a second. But that body will compress for a little bit, and then what's going to happen is eventually the fly will be going exactly the same speed as your hand. And because the fly was so light, he didn't take hardly any velocity out of your hand. So your hand was doing 107. Now it's doing 106.99 or something, right? So we actually accelerated that fly from 0 to 107 miles per hour. That acceleration would be 100 miles per hour minus 0 miles per hour divided by some amount of time. Well, the amount of time, which is probably on the order of how long it takes your hand to move, maybe about at most an inch, but I'm thinking more along the lines of a quarter inch or even a half inch. But that's the whole distance through which the fly speeds up, and it might even be just as small a length of space as the width of the fly or the length of the fly. So either way, that time period is very small, and that velocity change, 100 minus 0, is very big. So you get an acceleration that's made out of a pretty big number divided by a pretty small number. That's a pretty big acceleration. But if you look at Newton's second law, F equals ma, in that version, what you see is if this acceleration right here is super big, but this mass right here is super small, then the force is not going to be very big. So maybe the acceleration is on the order of 100 or even 300, but the mass in kilograms is on the order of 0.001. So that's 1/1000th. So we're basically taking maybe 300 or 400 and dividing it by 1,000 and therefore getting a very small force. So it's correct to say it the way I said it before, that the fly cannot apply a force on you any larger than you can apply a force on him. So if we flip that around, that says you can't apply a force on the fly any bigger than the fly can apply a force on you. All right. That is correct. But if you want to put, pencil to paper and figure out what that is, what you find out is that acceleration could be pretty big, especially compared to acceleration of gravity, accelerations that our astronauts deal with, that kind of thing. Maybe they're up to 10 g, which would be about 100 meters per second every second. We're talking here, the acceleration might actually be on the order of 100 g, or at least on the order of several tens of G's, so maybe 90 G or something like that. But when you take that acceleration and you then divide it by 1,000, which is what happens when you're dealing with a mass that's roughly a gram, then that number gets a lot smaller. So you see the force acting on the fly is actually quite small to bring it up to the acceleration such that it reaches 107 miles per hour. So hopefully that makes some sense. Anybody have any questions on how we can explain using Newton's third law why it's so hard to kill a fly in the air? So if you, it seems like you don't, but if you do use a fly swatter, then that takes your arm, which might be, you can sort of imagine it as doing a perfect circle like this. And I don't know if you've like water skied before, but if you water ski, when a boat goes in a circle at 30 miles per hour, if you swing out from it on your rope skiing in such a way that you're sort of keeping up with it, it turns out that in order for you to keep up with it, since they're only a radius of whatever the radius of the turn is, which might be, let's say, 100 feet, then at my radius, which is another 30 feet, another third beyond that, my speed can be a lot faster. So we often have people water skiing behind a boat going 30 miles per hour, and the water skier or the hydroslider or whatever they're doing, they might actually reach a speed of 60 miles per hour. So that same thing happens when you use a fly swatter and throw your arm like a pitch to hit a fly. So you might actually, by increasing that velocity so much, you might actually be able to kill them a little better, even again, just hitting it, the fly in the air as opposed to squishing it against something. Okay. But it's still the same problem as there. You're still trying to bring a small light object up to a really fast speed in a small amount of time. And that takes a fairly small amount of force. And that force might not be big enough more than to just, stun the fly or confuse them or something like that. Okay. All right. So those are Newton's laws of motion. And now I want to show you, how we go about applying them. Before we do that, I need to talk a little bit about the units that we're using. And I also want to stress the difference between mass and weight. So here's the three systems of units. We sort of use all of them, but to be honest, we're supposed to be sticking in the SI. The SI before SI existed was called the metric system, and in that system, a lot of people used what we called the CGS system, or I wrote it up here as the old metric system. But CGS just means centimeter, gram, second, and SI is considered the MKS for meters, kilograms, second. So just keep that in mind. So when you look at mass, obviously in the CGS system, that's supposed to be grams. When you look at the SI, even though there's a prefix in front of it, seems to be the only one that we have to deal with like that. That prefix still makes it the base one. Okay. So whenever we have an equation in our physics class, if it calls for mass, unless I explicitly tell you you don't have to use that particular mass, you've got to use it in kilograms. You can't use it in grams. Okay. And then if we're in the British system, which is what us and Myanmar uses, literally they're the only two countries. I'm pretty confident that it's Myanmar is the other one. It actually has a different name now, so it's might be politically incorrect for me to call it Myanmar, but I think that's the country I'm referring to, and I think it does have a different name. But in that British system, the unit of mass is called the slug. Uh, in acceleration, we know that's velocity per time. So in the centimeters or in the CGS system, it's centimeters per second every second. In the SI system, it's meters per second every second. And then the British system, it's feet per second every second. Uh, I haven't done much work in the British system, except for a little bit of engineering stuff where we work on kips and MIPS and GIPS, which is literally kilopounds, megapounds, and gigapounds. So even in the engineering world, where they still want us to stick, in many cases, still want us to stick to British units, they are definitely still using the tools of the SI by putting a kilo kip or a kilopound in place and calling it a kip, or a megapound in place and calling it a MIP, and a gigapound, which would be a billion pounds, as a GIP, GIP. Okay. The symbol that we use, of course, for force is the pound or the pound symbol. But the acceleration, like I said, is feet per second, or meter per second, or centimeters per second. And then if we use Newton's second law, the net force is equal to mass times acceleration. We can see that the units for force are just the units for mass times the units for acceleration, which we get gram times centimeter per second. This centimeter per second is the same as that. It's just mathematically, it's nicer to write it as an exponent of two. But I like you to think about it as centimeters per second because that turns out to be a little more physically reasonable and understandable. The unit in the CGS system of force is called the dyne. That's where we get the name dynamometer, and you might have heard that if you're into cars or motorcycles, or racing vehicles. You might have heard a dynamometer being used on an engine to figure out how much power it puts out. But to be honest, a dyne is a unit of force, not of power. There's a relationship between force and power. We'll learn that later, but the main thing is a dyne is a unit of force, and it's actually a very small unit of force. I'll explain that in a second. In the SI system, we use mass in kilograms. So we get kilograms, and then we have acceleration in meters per second every second. So we get kilogram meters per second squared, and that's called a Newton. Okay, so that's the unit of force in the SI is the Newton, and then in the British system it's the pound, which we write as LB or we write as the pound symbol. Now, just so you'll see that the dyne is a much smaller unit than the Newton, I wanted you to go ahead and understand what gravitational acceleration was in these three scenarios. So, in the gravitational acceleration, G is 980 centimeters per second in the CGS system. The one that you're more familiar with is 9.80 meters per second, and that's in the SI system. And then in the British system, it's 32 feet per second. Okay. And I think I've heard Sheldon in Big Bang Theory mention that a couple times. For the record, by the way, I'll write it this way: 1 pound is equal to 4.448 newtons. I think that's 8.3. It might be 8.2. It might be 8.4. It might be 8.6. I can't remember. But that's roughly what it is. So you can see that 1 pound or 1 newton is around a little bit smaller than a quarter pound. Okay, so a newton's still a fairly small unit. But if you realize that we're using 980 for G, you might see that you have a huge number of dynes to correspond to 1 newton. And in fact, you can see that it's times 100 for the centimeter per second, and it's times 1,000 for the grams to kilograms. So in fact, you'd expect it to be 100,000th of a dyne, or excuse me, of a newton. Let me get this other student that came in. So as I said, you can check yourself. 1 newton is equal to 10 to the fifth dynes. Okay. And like I said, that's because you're off by a factor of 100 for G and you're off by a factor of 1,000 for the mass. So that should give it to you. Now, I also want to talk about weight. Weight is the force of attraction between an object and its planet, moon, comet, whatever the big sort of celestial thing that it's standing on or sitting on or whatever. That big thing has a gravitational attraction to the person or the object. That object has a weight, and that weight is equal to the amount of force that the planet, object, celestial body is applying to that object to keep it on it. Okay. Mass, on the other hand, is a measure of a body's reluctance to accelerate, and it's called the inertia. I want to point out that a lot of people probably know this if they've been to the doctor's office. Uh, the doctor's office, they'll inevitably weigh you in pounds, and then they'll multiply that by 2.2 and write that down as your weight in kilograms. It's technically your mass. Like I said, kilograms are a unit of mass. A slug is a unit of mass, and a gram is a unit of mass. A pound and a newton and a dyne, they're units of force. So when you say you weigh, 100 pounds, that's the amount of force the earth is applying to you. That doesn't necessarily mean the amount of inertia you have. The amount of inertia you have has to be measured in slugs, or sometimes they'll use pound mass, which is just a made up thing so that they can make it a little more pleasing than calling people a certain number of slugs. Okay. But technically speaking, on an object, technically speaking, an object of mass 2.2 kilograms has a weight of 1 pound on the Earth's equator if it is at sea level. But strictly speaking, I left off a G here. Let me fix that real quick. Oop, I should probably fix it in blue. But 2.2 kilograms does not equal 1 pound. Okay, because they're two fundamentally different quantity. The kilogram's a unit of mass, the pound's a unit of force, so you can't say they're equal. What you could say if you wanted to is 2.2 kilograms. That was supposed to be a slug. I don't know why I wrote pound there. But 2.2 kilograms is 0.150748 slugs. Okay, so that's really a actual conversion factor. The good news is you can still use that because, to be honest with you, the acceleration of gravity doesn't change very much from the bottom of the Marianas Trench, which is the lowest place on Earth, up to the top of Mount Everest, which is the highest place on Earth. The swing in gravitational acceleration from top to bottom is only order of a few percent at most. Okay, so 2.2 kilograms being approximately equal to 1 pound is fine to use as an approximation. You just need to know that fundamentally they are entirely different quantities, so they're not technically equal to each other. Now that we have that, I'm going to go ahead and show you how to get the weight. So we learned earlier in chapter 2 in kinematics, and then we did it again in chapter 3 in projectile motion. We learned that an object in free fall falls without air resistance, right? So that means the only force causing an object to free fall is the force of gravity. So if I drew a ball up here and said its mass is m, and I said it's in free fall, does anybody know what its acceleration would be if it's in free fall? Anyone? It's called the acceleration due to gravity, and it has a very specific value. Exactly. If you chose Brianna, you're right. If you choose to call upward the positive direction, then you'd say the gravitational acceleration is negative 9.80 meters per second every second. That'd be exactly right. The magnitude of it is the important thing I'm shooting for, and A is just equal to G, which is 9.80. Notice that is 3 sig figs, meters per second. Okay? So I'm going to draw a free body diagram, which is what we're starting off with Newton's second law, and I'm going to show, let's treat this as our positive y-axis. Okay, that's weird. We're not used to putting the positive y-axis pointing down, but I don't like working with negatives. So as many times as I can, I point the axis down so I don't have to deal with any negatives, right? So what I'm going to do is I'm going to say, here's the force acting on it. It's the only force we know because it's in free fall, and free fall means there's no air resistance. And because there's no air resistance, it gets to experience the full acceleration of gravity. We know that this force is the weight, which I just defined as the gravitational attraction to the planet. Okay? So if I use Newton's second law of motion, which says the summation of all the forces acting on the body is equal to the mass of the body times A, Okay. And I cut it down to one dimension. I'd say the summation of the forces in the y direction is equal to mass times acceleration in the y direction, and y is down and positive. Then I know for a fact that the total force acting on it, because it's in free fall, there's no other forces, there's just the gravity acting on it. And that gravity we call the weight. So I'm going to put a W here. And then the object, which I already said had a mass m, so its mass will be m. And the object's acceleration, which we already said would be g, gives me g. So from that, we've managed to reach a conclusion about how we calculate weight. This is the formula for weight. And not only that, it applies everywhere. So if we go to the moon, then we need to find out the gravitational acceleration on the moon, which I think you know is about 1/6 of what it is on the Earth. And instead of 9.8 there, we use 9.8 divided by 6. And that would give you your weight on the moon. But notice your mass would be the same. So, for instance, I might have a mass of 100 kilograms. I wish, right? But anyways, whatever my mass is, let's say 110 kilograms, if I take that 110 kilogram fatty butt over to the moon instead of the Earth, my mass is still 110 kilograms, but my weight now is 1/6 of what it was on Earth. Okay. So your weight can change from going not only from one planet to another, but different elevations on the same planet or moon or comet or whatever. We'll learn that later when we learn about gravity. But now we have a formula for an object's weight. Does that make sense? All right. So now that we have all that, we can go about looking for an example. So, for instance, let's say you're riding down the street in your truck or your car or whatever, but I like a truck because it's got that flat bed in the back and it normally has like a bed liner that might be some cheap plastic and slippery. So you threw your book bag in the back of the truck. You take off, no big deal because you threw it in the back of the truck. It was right up against the tailgate, so it didn't move. But then all of a sudden, you come up to a stop sign or a stoplight and you hit the brakes, and what you see is your book bag slides from the back of the bed of the truck towards the front of the bed of the truck. What force caused that book bag to slide forward? Does anybody have an answer for that? Or is that a trick question? There you go. You're sort of honing in on it there, Brianna. Yes, it's not a force. It's more like what Galileo told us to make us feel better about smacking Aristotle around. Specifically, what we're saying is no, according to Newton and Galileo's law of inertia and Newton's first law of motion, which are identical, that is something that Newton definitely copied from Galileo. Uh, an object in motion tends to stay in that state of motion. So what happened was the truck might have been going 40 miles per hour, therefore the book bag was going 40 miles per hour as well. And then when you hit the brakes, the friction between the book bag and the bed of the truck was not sufficient to keep the book bag setting down in the back of the truck without moving. So, in fact, it tried to continue moving at 35 or 40 miles per hour. It was probably slowed down a little bit because the friction did something. It just wasn't zero. It wasn't like you had an ice skating rink in the bed. So it wasn't frictionless, but it was a lower friction than would be required to keep it sitting perfectly still. So, yes, its inertia made it continue to move, although it didn't move at the same 40 miles per hour the truck was going. Does that make sense to everyone? So, the mass, like I said, is a property. It's your book calls it a quantity of matter. I don't really like that too much, but in some sense, they're right. You're sort of taking the inertia of all the individual atoms or molecules that make it up and adding them all up, and then you get a net amount of inertia, and that's the mass of the object. But I just don't like seeing the quantity of matter because I don't really understand and never did understand when I was a student. Are we talking volume? Are we talking weight? Are we talking mass? Obviously, we must be talking mass because it's a quantity, but the word quantity of matter just didn't fill that in. So I sort of think of it as each of the atoms making up a certain object has an inertia. And since all things are made of atoms, then if you added up the inertia of all the individual atoms, then you would get the net inertia of the object, and that's what the mass is. So that's the way I think of it. You do whatever you need to think about it, but make sure it's consistent with the problems that you work, and then everything will work out. For Newton's second law, the big trick with this is you've got to break everything down into force components because Newton's second law, remember, if we look over here, Newton's second law, oops, not this one, is a vector equation. And the beauty of a vector equation is if you're in 3 dimensions, it's one equation that represents three. If you're in 42 dimensions, it's one equation that represents 42 equations. So in our life, until we study really seriously relativity, we're going to stick with our 3 dimensional world. And in our 3 dimensional world, Newton's second law becomes three separate equations. So in order to use it, we have to break each of the forces up into x components, y components, and z components, and each of the accelerations into x components, y components, and z components. But once you're down to that, then the Newton's second law is nothing but a real number equations with positives and negatives because the way you indicate the direction in one dimension is positive is one direction, the opposite is negative. So if you consider something like this, uh, actually, I'll do the same example I did in class earlier. Let's imagine we have a nice little tree. So we're going to have a nice little tree, and that little tree is right here. And then on this little tree, we have Bear in the big blue house. So that's supposed to be a blue color. So we have a little bear there. He's sort of bear hugging this tree like such. And what we know is that this bear has a mass. Let's see. I'm going to do some really quick math. This bear has a mass M. Actually, I should probably write that in the blue color. It has a mass M equal to 71.43 kilograms, and its weight W is equal to 700.0 newtons. So I'm saying all three of those figures are sig figs. Okay, that's why I put the decimal and the zero with a line under it after it. Now, what I'm also going to say is that there is a force of friction acting on the bear as well, and we usually use that fancy little F for friction. I'm going to say this particular friction force is 250.0 newtons, like that. And what I want to know is what is the acceleration of the bear as it slides down the tree. That's a pretty good bear. I like it. Anyways, so how do we go about solving that? Well, the first thing I'm going to do is draw a free body diagram. So a free body diagram is really the bare minimum to apply Newton's second law. But with time, you can even avoid doing that in some cases. I just don't recommend it. But it's a free body diagram. I know in different sections of dynamics and statics, they'll have free body diagram, and then they'll have like an acceleration diagram. We don't do any of that stuff. We just do a free body diagram, which shows just the forces acting on the body, and it might off to the side show in which direction the acceleration is, but it doesn't put it on the same graph because they're vectors that don't have the same units, and you can't even add them or anything. So a free body diagram normally includes a coordinate system. So I'm going to include a coordinate system. And I'm going to be weird again and call down the positive direction. So I'm going to say this is my positive y-axis, and I'm going to say this is my positive x-axis. And with that, I'm going to draw the bear as if he's a dot. When we get into rotational motion, we'll then be able to talk about objects that have a physical size, and then we can draw them as actual objects with a width and a height and a depth and that sort of thing. But right now, we sort of have to treat them as point objects. Because we don't really understand the concept of torque yet, which is the main thing. Okay. So now I draw all the forces acting on it. And what I try to do is I try to use something nice like green points in the positive direction and red points in the negative direction. So this force right here, which is green, is pointing in the positive y direction, and it's 700.0 newtons. There's also a force that points in the negative direction, and it's much smaller. That force, since it's in the negative direction, I chose to draw it red, and that force is 250.0 newtons. And then I also have to remind everybody that the mass is m. So now I've got the problem. It appears to be one dimensional. Since it's one dimensional, I can just write out the summation of the forces in the y direction is equal to mass times acceleration in the y direction, and I'm ready to roll. Now, we've got this standard of what's positive and negative, so this sigma means we're adding the forces. That's important to understand. I never subtract, but when you add a negative number to something, that's the same as subtraction. But really, what's going on is all the forces are being added. That's why we use the sigma, because that's the mathematical symbol for summation. Okay. So on the left, I'm going to put the sum of the forces, and the forces are positive 700.0 newtons plus negative 250.0 newtons, and that is equal to 71.43 kilograms times A. So we have one unknown here, and we can solve for that unknown, which is A. So the first thing I'm going to do is 700 minus 250 should be 450.0 newtons, and that's equal to 71.43 kilograms times A. So A turns out to be positive, which tells us it's going down. That makes sense, right? The force of weight was bigger than the force of friction, so you think the weight wins, and in fact it does. And I'm going to take 450 and I'm going to divide it by 71.43, and that gives me 6.29 or 6.300. And that answer is, remember, a Newton is a kilogram meter per second squared. So when I divide it by a kilogram, I just get a meter per second squared, which we call meter per second per second. Now, that's one extra sig fig there, and that's our actual answer. Okay. Now, I want to remind you that just because we got out of kinematics and stuff, they don't go away. So, I could ask part B, if the tree is really, really tall and the bear starts from rest, what distance will he have traveled in 1 second? All right. How about 2 seconds? How about 4 seconds? All right. If the bear started from rest, what would be its velocity after 1 second? What would be its velocity after 2 seconds? So all those kinematic equations can still be applied after that. Anybody have any questions on that one? All right, so that's a particular instance of applying Newton's second law of motion. And we've now seen a couple different ones, but let's look at another problem. Estimate the net force needed to accelerate a fast car. So let's say example two. A car has a mass of, let's say, 1,000 kilograms, and I'm going to call it 1,000.0 kilograms. And accelerates at A equals 1/2 g. Now, what I mean by that is 1/2 of gravitational acceleration. So I'm not saying a half a gram. I'm using a half of gravitational acceleration, which is 4.90 meters per second every second. And what we want to know is A, estimate the force required, and then B, uh, how much force would be required oh, that look bad. Would be required to accelerate a 200, let's say 200.0 gram apple at the same rate. In other words, the same acceleration. Okay. So let's start off with part A. So what we're doing here is we're just trying to think. Let's ignore all the different forces that could come up, and let's just think if we were able to do this in somewhere where air resistance wouldn't be an issue, what would be the force required? So what I'm picturing here is an object whose mass is m is equal to 1,000.0 kilograms. I'm going to draw a coordinate system where this is my positive x-axis. I don't even need the y-axis, but I'm putting it there just for completeness. What I am going to do is say that there's a force acting on it in the positive direction, and that force is, in this case, I feel compelled to draw it behind it like it's pushing it ahead. But the main thing, it's still pointed to the left, which is the direction the object's going. So that F is what we're trying to get. Okay, but that's the free body diagram. Technically speaking, we do know that there's a normal force acting upward, and we call that F normal. And we also know that there is a weight acting downward, and we call that W. But the summation of the forces in the y direction equals mass times acceleration in the y direction. We're not expecting this car to jump up real fast or to dig into the road, so we're expecting the acceleration in the y direction to be 0. So we get Fn, which points up, minus W, which points down, is equal to m times 0. So we conclude that the normal force is equal to the weight. We didn't need that, but later when we study friction, we will. So I'm showing you how that's done. Now I need the summation of the forces in the x direction is equal to mass times acceleration in the x direction. And the acceleration we already know is 4.90, but the force is what we're wanting to know. So I'm going to write in that I have a force F, that's the only force, that's equal to 1000.0 kilograms times the acceleration, which is 4.90 meters per second every second. So therefore, we conclude that the force, again, we're doing an estimate here, so we're sort of assuming the air resistance and all that stuff is zero. What we end up getting is multiplying this by 1,000. It turns out that we get 4.90 times 10 to the third newtons is the force. Now, if we divide that by 4.44, so I'm going to say 4.90 times 1,000. That's what we just did. We got 4,900. And now I'm going to divide that by 4.4483 again is what I think it is. And that gives me approximately 1,102 pounds. So that's the force required to accelerate a 1,000 kilogram car uh, at 4.90 or half of g. Any questions on that one? Now, part B is going to be even easier because it's again, force is approximately equal to M times A, but in this case it's 200 grams, so it's 0.2000 kilograms times 4.90 meters per second every second, and that gives us zero point 0.2, well, zero point 0.2 times 4.9 gives me 0.98. And in that case, it's 0.9800 newtons. And I'm working that out as pounds. And that is about equal to 0.220 pounds. So you can see it takes a lot less force, obviously, to accelerate an apple at 4.90 meters per second every second. Anybody have any questions on that one? Okay. So now that we have a little bit of idea what's going on with Newton's second law, let's try another problem. In this case, I'm just going to draw it out. So this is going to be example. What I have here is a box whose mass is 10.00 kilograms, and then another box whose mass is 5.00 kilograms, and then another box whose mass is 3.00 kilograms. And I'm applying a force of F equals 400.0 newtons. And these boxes are all chained together like a little train. So, what I would like to know is this is going to be called T5 and this is going to be called T10, and they're tensions in the rope. So what I'm asking you is when I apply a force of 400 newtons to this chain with no friction, by the way, I want to know what acceleration the train will get. Again, treating it like a train. And what is T5 and what is T10? Okay. So first off, we can treat the whole body as a single body, and I will draw a coordinate system like this. That's going to be my positive x direction. This is not really going to be relevant, but it's going to be my positive y direction. And what I'm saying happens here is this object right here is the train, and I think you can see that its mass is m equals 18.00 kilograms. And I think you also see that the force acting on it is F equals 400.0 newtons. So we can figure out that the summation of the forces in the x direction is equal to 18.00 kilograms times A. Okay, that's the summation of the forces in the x direction is equal to acceleration in the x direction. Now, in each of these cases, we've got basically a weight 18 times 9.8 acting down and a normal force Fn acting up. But just like we did above, all that turns out to say that the weight is equal to the normal force. So it's not relevant. We're not having any acceleration perpendicular to the plane or anything like that. So from this, we can get that A sub x is equal to 400.0 newtons divided by 18.00 kilograms. So when I do that, 400 divided by 18, I get 22.22 meters per second every second. And we really only had 3 sig figs, so that's that one. So you see, that's a really huge acceleration. That's almost as big as the acceleration of gravity on Jupiter. Okay, so that's a really big deal, but it's not that big a deal because all we're doing is making up a problem so that you can understand how Newton's laws of motion works. Now, what I have to do to find out the individual tensions is by treating the whole object as one object, I can't solve for the inside forces because they're part of the system, right? But if I draw a free body diagram for each of them, what I'll get is, and actually I should have drawn that a little differently. I'm going to draw a axis like this. This is my positive x-axis. I'm going to draw a mass right here that is, now that one's 10 kilograms. 10 kilograms times 9.8 is 98.0 newtons. And then uh, I'm calling, actually, that should have been red because that points down. And then I'm saying the normal force points up, and that's going to turn out to be exactly 98 newtons. But we also have a force pointing in this direction, and that force is T10. We have over here another mass. Now, this mass right here was 10.00 kilograms. This mass right here is 5.00 kilograms. Again, it has, in this case, 49.0 newtons acting downward and a force acting upward that's force newtons sub 5, whereas this one was sub 10. But again, that one's going to be, those two vertical forces are going to cancel out. But I am going to have a force this way, which is T5, and a force this way, which is T10. Okay? And then the last mass, of course, is the 3 kilogram. And acting on it, of course, is 3 times 9.8. And I don't want to make up mistakes. That's 29.4 newtons acting downward. The normal force has to act upward and has to just cancel that out. So that'd be F normal sub 3. But in this case, we've got a force pulling forward that was 400.0 5.0 newtons, and we also have a force pointing backwards that is T5. So we're down to 2 minutes. I'm going to start off with one, the summation of the forces. So this is the 10 kilogram object. The summation forces in the x direction equals mass times acceleration in the x direction. In this case, that gives me T10 is equal to 10.00 kilograms. Now, because we're not assuming the ropes get slack or they stretch or anything, then the acceleration of the 10 kilogram block has to be exactly the acceleration of the whole thing. So the acceleration is going to be 22.22 meters per second every second. So that gives me that T10 is equal to 222.2 newtons. Now for the other one, the 5, we have the summation forces in the x direction equals mass times acceleration in the x direction. And this is for the 5.00 kilogram object. In this case, we have T5. Remember, that one points to the right, so we're looking right here. The T5 points to the right and the T10 points to the left. We just figured out what T10 was. That is 200, oops, got to change it back to the color. That's 222.2 newtons, and that's equal to 5.00 kilograms times 22.22 meters per second. So from this one, we can get that T5 is equal to 5 times 22.22 is 111. Now I got to add to that 222.2, and that gives me 333.3 newtons. So that's how T5 can work out. And just for checking, you can go ahead and do the 3 kilogram object like this, 3.00 kilogram. In that case, we had the summation of the forces in the x direction equals mass times acceleration in the x direction. We had 400.0 newtons minus T5, which is 333.3 newtons. That's equal to 3.00 kilograms times A. So we're going to verify that our A is right. A should be equal to, what's that? That's going to be 66.67 newtons divided by 3.00 kilograms. So 400 minus 33.3 gives me 66.67 if you want. Now I'm going to divide that by 3, and that gives me 22.23 meters per second, which is a great check, and it worked. Okay? So that's sort of the crux of how you go about working with the Newton's second law. You guys are free to go. I wanted to work an Atwood machine for you, so I'm probably going to work that once everybody that needs to leave leaves. It'll be on the end of the video, so you can still check it out. But go ahead and chat me your first and last name. You guys are free to go. Just remember, at the end of the video, there's going to be another little short problem that I'm solving. Thanks for coming, everybody. I'll wait for the last person to leave in case anybody has any questions, so feel free to ask me questions. That was example 3. I'm going to do example 4 in a second. All right. It looks like probably everybody that is leaving has left, so I'm going to go ahead and do what I was working on before. So I'm going to solve what we call the Atwood machine. And this is going to be an Atwood machine with a massless pulley and a frictionless pulley. Okay. Later on, we'll address it having a mass, and we'll address it having a friction as well. But right now, I just wanted you to get another idea of how to apply Newton's second law. So what I'm going to do is I'm going to use my helpful drawing tool in my good notes, and I'm going to attempt to draw a circle to represent the pulley. And look at that perfect circle I drew. I am amazing. Now I'm going to extend a rope from it. That's going to point straight down. And now I'm going to put a mass on the end, and that mass is going to be represented by a capital M because I want you to think of it as a really big, heavy mass. Okay. And then on the other end, I'm going to put way, way down low a mass little m, and that's going to represent, as you might suspect, a mass that's kind of small. So just from the drawing, I think you can see that we're expecting this big mass M to go down to the left, and that's going to cause the mass little m to go up on the right. So a lot of people will attack this problem by trying to solve it like we did in the first step of the train, where we treat it as one object. Do not do that. There's so many pitfalls with that, and I never even try it, to be honest with you. I've done it a couple times just to see that I could, but it was a nightmare and it was hard to solve. So we're not going to do that. What we're going to do is we're going to draw a free body diagram for each mass, and we're going to apply Newton's second law to it in each case. And I'm going to explain, you've got to listen to all the words I'm saying here. These words are very, very important because they make everything make sense. So it looks to me like the mass big M from the drawing, we are expecting it to go down. So what I'm going to do is I'm going to say there's a positive x-axis pointing down on the right. So let me draw my free body diagram. I'm going to say this is for mass M. This is the free body diagram for big M. Okay. Now, what I'm drawing here is a downward axis that I'm going to call the positive x-axis. And then I'm going to draw a point particle for the mass. This is the mass. It has a mass of big M. Now, when we go to think about forces, the first thing we think of is everything that's touching the object of mass M can apply a force. Right now, the only thing we see touching the mass M is the cord or the string, okay? And when a force is applied through a rope or a cord or a string, we call that a tension, T as in tension. So, since that if you were actually on that mass big M and you were actually riding it as it played out, what you would say is, oh, wow, I'm sitting on this box and it's falling towards the earth. And luckily, there's this rope right here because this rope is slowing me down, or otherwise, I'd be falling at 9.8 meters per second every second. So it must be that rope slowing me down. So that means the tension must be pointing upward, and that tension we're just going to call T. Okay. Since it's pointing upward and I call down as the positive direction, then T is going to be in the negative direction. So that's why I drew it red. Now, the other force, once you've eliminated everything that's touching it, the only thing that's left are those weird actions at a distance. And we haven't talked about those before, but those are forces like gravity. Like right now, I'm not touching the earth. I'm on my floor, which is on joists, which are sitting on pilings, and the pilings sitting on the earth. So the earth is not touching me, yet I still have the weight applied to me. That's action at a distance. It's applying a force to me without touching me. So we have to then take into account, once we've done all the objects that are touching it, we have to take into account the action at a distance, which is a gravity force, electric force, nuclear force. We'll later learn about a strong nuclear force, and that kind of stuff. So right now, I'm going to say the force acting downward, which is our positive direction, is our weight, and we just derived the formula for weight. We know that the weight is equal to capital M lowercase g. So I can now write Newton's second law, the summation of the forces in the x direction equals mass times acceleration in the x direction. I'm going to make an argument in a second that makes you understand why there's really only one acceleration here, so I'm not going to subscript it. I could subscript it left or subscript it capital M. We don't need to, and I'll show you why in a second. So now all I have to do is put all the forces added up on the left. That would mean mg, which is positive, pointing to the pointing down obviously is positive, and then I'm adding to it the tension T, but that's in the negative direction, so I'm going to say plus negative T. And that's equal to the object's mass, which capital M, and times the object's acceleration A. So what we want to know is A is the unknown and T is the unknown. Okay? Now, here's the part where I need you to listen as well. In addition to what I've already done, there were some very key words that happened there, but there's also some key words here. If I were to take the mass big M and pull it down 1 inch, if we assume that the string doesn't stretch or get slack, which is the assumption we're going to go on, then the mass on the right would move up 1 inch as well. So we can see that position according to the moving of the position of mass big M is exactly the same as the delta x of little m. So delta x for big M is the same as delta x for little m. Now, it would be the negative of it if we didn't use a coordinate system completely consistent. And then we'd have to make up an equation to relate the coordinate system on the left with the coordinate system on the right. But if I choose to make downward the positive direction on the left and upward the positive direction on the right, then we'll have a consistent coordinate system so that delta x on the left is exactly equal to delta x on the right. Otherwise, it'd have to be delta x on the left is equal to negative delta x on the right. So pulling the left side down 1 inch equates to the right side going up 1 inch. Now, if I went and pulled the left side down 1 inch in 1 second, the right side would go up 1 inch in 1 second. So that tells me the velocity on the left will be equal to the velocity on the right. That's good. That's kind of helpful. And again, if I had done it with the reverse coordinate systems, it would have been the velocity on the left is equal to the negative of the velocity on the right. We don't want that because that's just another equation, another pain in the butt. Now, if I also consider pulling down on the left 1 inch in 1 second and then 2 inches in the next second, then the right-hand side will go up 1 inch in the first second and up 2 inches in the second second. And we now know that the acceleration on the left is equal to the acceleration on the right. And that's why I don't have to write a different acceleration. Okay? Now, there's also a reason we don't have to write another tension, because what you can think of is the tension on the left is what's slowing down the mass. Okay? But the tension on the left is responsible also for rotating that pulley counterclockwise. But that pulley is massless and frictionless, so that equates to nothing. In which case, that tension, which would normally rotate the pulley counterclockwise and lift up the mass, little m, on the right-hand side, since the mass of the pulley is zero and the friction of the pulley is zero, the tension in the left has to be equal to the tension in the right. So that's why we don't have two tensions. Now I'm going to use all of those words I put together, and I'm going to make the free body diagram for lowercase m. Again, we're pretending we know M, we're pretending we know big M, we're pretending we know G. The only things we don't know are T, the tension, and A, the acceleration. We did choose, since the left side going down was the positive x direction, we chose to make the right side going up the positive x direction so that we'd have A left equals A right. Okay? So now I'm going to put the mass right here. In this case, the mass is little m, and the force acting on it in the upward direction this time is the green one. Oops, wrote it wrong way. Is the green one. And in this case, that is the tension. Again, it's the same tension on the left as it is on the right, because the only thing that would make them different is the fact that the tension on the left has to lift M and rotate the pulley, whereas the tension on the right just has to lift M. Now, the force acting in the downward direction on this side is in fact the weight, which is equal to little m and little g, or excuse me, little m times g. Now I take the summation of the forces in the x direction equals mass times acceleration in the x direction. Again, I've already showed you how the accelerations on the left is equal to the acceleration on the right, so we don't need two accelerations. Now I'm just going to sum up the forces, and the forces are positive t. I don't know why I wrote it in green, but I did. Plus the other force. The other force is in fact negative lowercase m times g, and then the right hand side is just m times a. Okay, so I'm going to call this equation 2, and I'm going to call this equation 1. Now, what I have is a system of two equations, two unknowns, and it turns out when you have them like this, where t is negative in one equation on the left-hand side and t is positive on the other equation on the left-hand side, the one of the smartest, easiest ways to do it is add the left-hand sides of equation 1 and 2 to get a new left-hand side, add the right-hand sides of equation 1 and 2 to get a new right-hand side, and we'll get a new equation and therefore eliminate t. So adding 1 and 2, we get mg plus negative t plus positive t plus negative mg. That's the left-hand side. The right-hand side is equal to ma plus ma. So you can see automatically that the plus t and the minus t cancel each other out. And you can also see that there's a common factor of g on the left now, and there's a common factor of a on the right. So I can go ahead and write that m minus m parentheses times g is equal to m plus m in parentheses times a. So I can solve for a, and I'll get m minus m over m plus m, all of that times g, which is the best, most perfect way to actually list an equation, because you have a quantity in parentheses that has no units whatsoever. Mass minus mass gives you units of mass. Mass plus mass gives you units of mass. Mass divided by mass gives you no units. So the whole parentheses has no units. And A, which is an acceleration, therefore is equal to a unitless number times g, which obviously has units of acceleration. So it tells us everything we need to know in the most beautiful way possible. Now, if you now take this a and plug it back into equation 1 or 2, then you can solve for t. I'm going to plug it into 2 because it has the t already on the left and has it positive, so I don't have to divide by -1 or anything. So I'm going to say plug a into equation 2, and what I'm going to get is t plus negative mg is equal to m times m minus m over m plus m times g. So I can write this as T minus mg is equal to m minus m squared over m plus m, all of that times g. Now, in order to combine the mg, I'm going to pull it, the lowercase mg, I'm going to pull it over here and then get a common denominator. So what I end up getting here is T is equal to, now I have a M times M plus M over M plus M times G, and I have what was already there, which was a M, oh, excuse me, that's plus, sorry about that, which is a M minus M squared over M plus M times G. So we can just sort of let that G float out to the right. And now I'm going to distribute. I get M plus M squared. Again, leaving the G outside, I'm going to add this to the denominator in the second fraction, which is plus M minus M squared. All that has the common denominator M plus M, and then all of it's multiplied by G. Now, what you should be able to see is this m squared is negative and that m squared is positive, so they're going to cancel each other out. And finally, we're left with the result that t is equal to, and I'm going to write it a very specific way. I'm going to say t is equal to 2 times big M over big M plus little m times g. So the reason I wrote it this way is the same reason I wrote the last one the other way. The 2m over m plus m has units that are basically has no units because the 2m has units of mass, the m plus m has units of mass, so 2m divided by m plus m is mass over mass, which cancels out and gives you no units. But the mg has units of force, and a tension is a force, so it's really convenient because we can immediately see that this object has this equation has exactly the units we expect it to. So that's how you go about solving the Atwood machine for both variables. And this will come in handy. We'll see other times where equations will come up with the exact same form. We'll see other times we're doing more complicated Atwood machines on inclined planes and stuff, and we can make them reduced back to the same form so that we'll know that the answers we got in this new realm is exactly right. But that's it. I just wanted to give you one more problem from Newton's second law before I called it a day. So that makes it a day. Everybody have a good one, and thanks for coming. And that's the end. Now I'm stopping sharing, and now I'm going to say bye bye. Have a good day.